Hey guys, this is Mr. C. In this video, we're going to talk about discrete exponential functions. So discrete exponential functions are exponential functions that grow or decay exponentially, and they only go by certain amounts. So the domain is going to basically be the set of natural numbers or integers. It's not going to be all real numbers. So it's going to go up by a certain amount each time. And the first example, you're going to see that right away. It says the number of ants observed on an ant farm is shown in the table below. Graph the data on the graph on the right. And it says days and number of ants. Well, you can't really have half of an ant sitting there and have it be an actual, ant that's going to produce more ants. So it's either got to be a whole ant or none. And so since we're talking about whole ants here, then that's going to make this discrete. So you can't go in between numbers in your domain. That makes the most sense probably. And we've already talked about discrete functions for linear, but now we're going to talk about for exponential. All right, so we have the table of values here. At 0 days, there are 2 ants. And so on our graph, it looks like all of these numbers here are positive and these are all positive. And that's going to restrict us to quadrant 1 up here. So all of this part of the graph isn't even going to be used. Let's go ahead and talk about what we want to do with our labeling of the graph over here. I think I'm going to go by tens each one of these marks here. 10, 20, 30, 40, 50, and then 60 up there. And then I think I'm going to go 0, 1, 2, 3, 4, 5, 6. So my domain here is going to be the number of days or time, and then my range here is going to be the number of ants. So we got the input, days, output, ants. And this is independent, just to remind you of that. And here we have dependent. The more times you see this, the better. All right, so 0 days, 2 ants. So I'm gonna have to figure out where 2 ants are on here. And it's probably gonna be somewhere about down there. Now we have 1 day, 4 ants. That's a little bit less than halfway though, if each one of these marks is 10 ants. 2, 8, getting closer up to 10. 3, 16, now we're starting to grow a little bit. So 16 is gonna be just a little bit more than halfway between these 2 boxes. Now we have 4, 32, that's definitely gonna be way up here. And you see the curve start to curve up dramatically right after not a very long period of time. It starts to really go up. That's what exponential functions do. And then you have 5, 64. If 60 is way up here, then 64, we might be able to get away with it about right there. So here's our number of days and here's our ants, and you can clearly see this pattern going up quickly, and that's what we call exponential growth. Assuming the pattern continues, after how many days will the ant population exceed 2,000? That's a good question. After how many days will it exceed 2,000? So at 5 days, it's 64. It looks like it's doubling each day. So at 6 days, you would double the number of ants. So if you take 64 and double that, you get 128. All right, at 7 days, you double it again. And so if we multiply that by 2 again, we're gonna get 256. At 8 days, another doubling. So multiply that by 2 and you get 512. Okay, at 9 days, another doubling. Multiply it by 2 again and you get 1024. But we're still not exceeding 2,000 yet. But if we do one more, multiply by 2, you get 2048. And now we've exceeded 2,000. So assuming the pattern continues, after how many days will the ant population exceed 2,000? We definitely now know that the answer is 10, after 10 days. All right, so now we got problem number 2 here. And it says, a ball is dropped from a height of 6 feet. After each bounce, the maximum height of the ball is 2/3 the maximum height of its previous bounce. Complete the table below, and it says write a discrete exponential function to model the situation and graph the function. kind of tough things to do, but we can do it. So number of bounces, 0. So at 0 bounces, the height of that ball, if it hasn't bounced at all, is dropped from a height of 6 feet. So that's an initial height. So we're going to get a 6 feet right there at the very beginning. Then after one bounce, it's going to go 2/3 the maximum height of the previous bounce. So to get that value, we're going to take 2/3, multiply that times the previous number, and then that's going to give us our next one. So if we take 2/3, which is 2 divided by 3, going to get a decimal, times 6, and it gives us 4. All right, let's do it again at 2. So what's going to happen now is you're going to take now the previous 4, and again, you're going to multiply it by 2/3. And so if you do that, and I'll do this one, 2 divided by 3 again equals, times 4 equals, and you get about 2.6 repeating, which is going to be approximately 2.7. Okay, so if you continue doing this, replacing this number down here for the next one and then multiplying by 2/3, here's what we're going to get for our pattern. The next one is going to be about 1.8. The next one is going to be approximately 1.2. The next one is approximately 0.8. The next one is approximately 0.5. And the last one is approximately 0.4. All right, so now we're going to go ahead and graph that. So 0, 6, 0, 6. Okay, that one's done. 1, 4, 1, 4. So it looks like it's going down, definitely. Okay, 2, 2.7. It's going to be almost a 3, maybe right there. 3, 1.8. It's about right here. 4, 1.2. 5, 0.8. 6, 0.5. And 7, 0.4. So what you have now, and my dots aren't perfect, but it's pretty close, is what we call exponential decay, where instead of going up, it's going down. As the independent variable gets bigger, the dependent variable gets smaller. So the number of bounces increases, the height of the ball is going to decrease because you didn't get the full bounce every time, you only got 2/3 of it. So it's going to keep going down by the same amount with ratios this time. All right. Now, we want to write a function for that. So how do we write a function for this? Well, the way you do that is we're going to put y is equal to, and y is the output, the initial height of 6 times 2/3, which is how much you're going to get after every bounce. And then you're going to raise that to the x power. And so x is the number of bounces, and y is the height after those bounces. And there's the function you would write. You have to do this in the EOC quite a bit. All right, now let's go ahead and take a look at some, there we go. Now we're going to look at some tables of values. It says to complete the table of values for each function. Here you have f of x is equal to 2 to the x. This is just to get you used to be able to coming up with values here, how to actually find these numbers to put in these tables so you can graph them. Okay, so for this one, 2 to the negative 3. 2 to the negative 3 power is going to be 1 over 8. And the reason why is because 2 to the negative 3 is actually equal to 1 over 2 cubed by the rules of exponents. And then that's going to be 1 over 8. Negative 2, give me 1/4. Negative 1, 2 to the negative 1 is 1/2. 0, 2 to the 0 power is 1. 2 to the first power is 2. 2 2 squared is 4, and 2 cubed is 8. And that table is done. Okay, for our next one, okay, this time you can let the calculator do some of this for you depending on if you want decimals or not. I don't really like decimals too much unless I have to use them to graph. If I want to find out what -3 is for that x right there, let's just do that one. 2 times 3/4 to the -3. Well, what that's going to be is 2 times, we take the 3/4 and flip it 4/3, and we make it a +3. That's the rules of exponents. Then we're going to take the 4/3 and cube each one of these. That's going to be 2 times 4 cubed is 64, and 3 cubed is 27. And then finally, 2 times 64, the numerator, is 128 over 27. And so the final answer here would be this one is 128 over 27, which is good for the number, but not very good to graph. If you wanted to graph these, then you'd have to get decimals for these probably on your calculator. -2, doing the same process you did here, is going to give you 32 over 9. -1 is going to give you 8 over 3 if you did the same process that you just did here. 0, 3/4 to the 0 power is 1 times 2 is still 2. And now you have just 1. 2 times 3/4, because 3/4 to the first power is just 3/4, would be 6 over 4, which is what, 3/2? Squared would be 9 over 16 times 2, and so that should be 9 over 8. Cubed would be 27 over 64 times 2, so that would just be 27 over 32. And that one's done. This one over here is decimals, so we're going to keep it as a decimal. And we'll go ahead and do this one on the calculator just to see how it works in the calculator. So 0.6 raised y to the x raised to the -3 is equal to, and then multiply by 0.8. And that's going to give you about 3.7. Okay, let me do that one again just to make sure that you got that. So you take 0.6 the base, y to the x raised to the 3, make it negative, equals, and then multiply by 0.8. Same number. All right, let's do -2. 0.6 raised to the 2, make it negative, equals, times 0.8, and that's about 2.2. Let's try -1. 0.6 raised to the 1, make it negative, equals, times 0.8, and that's about 1.3. 0 is pretty easy. 0.6 to the 0 is just 1, times 0.8 is just 0.8. First power would just be 0.6 times 0.8, and that's 0.48. Squared, 0.6 raised to the second power, times 0.8, and that's about 0.288. I guess we can write all three of those down since it terminates. And the last one, 0.6 raised to the third power, 0.216, and then times 0.8 is 0.1728. And there is your table for the third one from the calculator. Okay, so now we have a word problem, which the EOC is very fond of. It says, suppose you do a favor for 3 people. Then you ask each of them to do a favor for 3 more people, passing along the request that each person who receives a favor does a favor for 3 more people. Suppose you do your 3 favors on day 1, each recipient does 3 favors on day 2, and so on. How many favors will be done on day 10? All right, so let's take a look at this. So what I want to do is make a t-table. And I'm going to do days in this column. And then I'm going to do favors over here. Okay, on day 1, there are 3 favors, right? Because I'm just doing 3 favors just myself for 3 people. Okay. On day 2, each of those 3 people is going to do 3 more for each one, making a total of 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. On day 3, each of those people are going to do 3 more, and that's going to make it 27. So what's happening each time is it looks like we're multiplying the previous number by 3. And that's exactly what happens for an exponential function. On day 4, we're just multiplying by 3 each time. 27 times 3 is 81. On day 5, that's going to give us 243. Day 6, and we can go all the way up to 10, really, because that's not too hard to do. 8, 9, 10. We just multiply by 3 each time. So let's do 243 times 3, 729. Okay, do it again. Times 3, 2187. Times 3, 6561. Times 3, 19683. One more time. Times 3, 59049. And that is how you create an exponential function. And this function is going to look like this. F of n is equal to the initial amount of 3, the base is 3, or the number of favors that's done each time. And that's just raised to the nth power. And n would be the number of days. So if we wanted to find the 10th one right away, if we had written this down, all we'd have to do is just take 3, raise it to the 10th power, and boom, there's your answer right there, instead of writing down all of this stuff. But then you would have to know all of this and have that knowledge to be able to write this function. All right, guys, so that has been discrete exponential functions. Remember to like my videos and subscribe to my channel if you haven't already. We'll see you guys later. Bye.